Good day, everybody. How are you all? Hope you're doing great today. So we are going to discuss central limit theorem. The central limit theorem. The central limit theorem, CLT for short, is one of the most powerful and useful ideas in all of statistics. There are two alternative forms of the theorem, and both alternatives are concerned with drawing finite samples of size small n from a population with a known mean mu and known standard deviation sigma. The first alternative says that if we collect samples of size small n with a large enough n, calculate each sample's mean, and create a histogram of those means, then the resulting histogram will tend to have an approximate normal bell-shaped. The second alternative says that if we again collect samples of size small n that are large enough, calculate the sum of each sample and create a histogram, then the resulting histogram will again tend to have a normal bell-shaped. So let me explain with an example. Suppose I want to find out the mean age of all students at a college with a population size of 10,000. I cannot reach 10,000 students at all time. Suppose I draw simple random samples of size 36 from this population of size 10,000, and I draw several samples of the same size 36 from this population. From each of these sample, I ask everybody, like 36 students, what is your age at your last birthday? So I add all the 36 numbers and divide by 36, I get the sample mean. So you say if I have 36 samples of size 36 each, then I have 36 values of X bar or sample mean. I can plot those sample means on the horizontal axis, divide the sample means into groups starting from the small number, groups of equal width up to the largest number, largest sample size. Okay. Suppose there are eight groups there. Then I will have 8 vertical rectangles on top of each of these groups of equal width. Okay, so if the smallest sample size is say 18, I can have the first group from 18 to say 22, and there will be a vertical rectangle on top of this group from 18 to 22. What is the height of this vertical rectangle? The height of this vertical rectangle is equal to the relative frequency, or what percentage of the entire samples of size 36. Remember, I have 36 samples of size 36 each. What percentage of those entire sample of size 36 falls in the first group between 18 and 22? So the height of these bar is proportional to the relative frequency or the percentage in the first group, and so forth. So each of these groups will have a vertical rectangle on the top of it, and the height of the rectangle is equal to the relative frequency or percentage in that group. Then if I join the top roofs of these vertical rectangles, I will get a bell-shaped curve, similar to the normal distribution. Actually, it's a normal distribution, it's a bell-shaped, okay? Moving forward, in either case, it does not matter what the distribution of the original population is or whether you have even need to know it. The important fact is that distribution of sample means and sums tend to follow the normal distribution, the bell-shaped curve, like I said. The size of the sample n, remember my sample, each sample was of size 36, that is required in order to be large enough depends on the original population from which the samples are drawn. The sample size should be at least 30 or the data should come from a normal distribution. That's why I selected a sample of size 36, which is greater equal to 30. The central limit theorem for sample means averages. Suppose X is a random variable with a distribution that may be known or unknown. It can be any distribution. Using a subscript that matches the random variable, suppose mu is the population mean, small m in Greek language, mu sub x is the mean of x. Sigma sub x, sigma is small s in Greek language, mu x is the population mean, and sigma x is the standard deviation, population standard deviation of x. In my example, x was age. If you draw random samples of size n, in my example it was 36, then as n increases, that is as sample size increases, the random variable x bar, sample mean age in my example, which consists of sample means, tend to be normally distributed, bell-shaped. So x bar is a normal distribution with a mean mu x, which is the mean of the population. And the standard deviation of x bar, or the probability distribution of x bar, is sigma, which is sigma x, which is the population standard deviation, divided by square root of n. Sigma x divided by square root of n is called the standard error of the mean. So what did we learn from here? I told you if you join the top roofs of the vertical rectangles on top of each group, height of each group is relative frequency, you get a bell-shaped curve. The center of this bell-shaped curve, where the peak is the highest on the horizontal axis, is equal to the mu sub x, which is the population mean. But the spread of the distribution is smaller than the spread of the population from which the sample came. Why? Because it is the population, its standard deviation is the population standard deviation sigma x divided by square root of n, square root of sample size. And this sigma x by n, square root of n, which is the standard deviation of the probability distribution of x bar, is called the standard error of the mean. The central limit theorem for sample mean says that if you keep drawing larger and larger samples and calculating their means, the sample means from their own normal distribution. So the probability distribution of the sample mean is also called the sampling distribution. Why? Because it comes from a sample characteristic. That's why it is called sampling distribution. To find probabilities of the means for the calculator, follow these steps. Okay, so it's very simple. It's similar to what we did previously. We will use second verse 2, which is normal CDF. Second verse gives you distributions. Number 2 is normal CDF. Then in the arguments, we have the lower value, which if you are less than some value, lower value will be minus 1 E99, upper value will be that value. You know the mean of the population, but don't forget to divide the standard deviation by the square root of the sample size. Where mean is the mean of the original distribution, standard deviation is the standard deviation of the original distribution, sample size is n. An unknown distribution has a mean of 90 and a standard deviation of 15. Samples of size n equal to 25 are randomly drawn from the population. Okay. Unknown distribution. So we do not know whether whether the population itself is bell-shaped in nature. Okay. So if the population is bell-shaped in nature, if we do not know that and the sample size is less than 30, then I would hesitate to assume that the mean of the sample means that the probability distribution of the sample means or the sampling distribution is bell-shaped in nature. Okay. In the 7.1, now we are drawing a sample of size 30. So we can assume the sampling distribution is bell-shaped in nature with the mean equal to 45 and the standard deviation is 8 divided by square root of 30 and so forth. Okay. So they again go through percentile. Remember, percentile is the area to the left of K. So if it is 20th percentile, area to the left of this unknown value of sample mean is equal to 0.2. And then the mean, and then don't forget, divide the standard deviation by square root of sample size. I have worked out some problems. I will provide links to those videos too. In a recent study reported on October 29, 2012, on the Flurry blog, the mean age of tablet users is 34 years. Suppose the standard deviation is 15 years. Take a sample of size n equal to 100, which is greater than 30. What are the mean and the standard deviation? The mean of the sampling distribution is equal to the mean of the population, which is equal to 34. And suppose the standard deviation is 15 years. Take a sample of size 100. So the standard deviation of the sampling distribution or standard error of the mean is the standard deviation of the population 15 divided by, then you do second button and excess square button in TI-84 gives you the square root. Inside the square root, sample size 100 and it is 1.5. Find the probability that the sample mean is more than 30 years. More than 30 years means you are on the right of 30. So you go second, verse 2. Lower is not -1 E99. Lower, you're starting from 30. Your upper is 1. Then second comma gives you the E99. What is your mean? Mean is equal to the mean of the population, which is 34. What is the standard deviation? It is 1.5, remember. Because you're using the standard deviation of the sampling distribution or standard error of the mean, which is the standard deviation of the population 15 divided by square root of sample size, which is 100, which gives 1.5. And then you paste, enter and enter. And that is 0.996. Then they ask us to find the 95th percentile of for the sample mean age. So you do second, verse 3 now, in norm, because you know the area to the left, which is 0.95 because it's 95th percentile. The mean is equal to the mean of the population, which is 34. The standard deviation is 1.5 and you paste, enter and enter. So 95% of the data are below 36.47 or 36.5. Okay, and so forth. Central limit theorem, similar idea. Suppose X is a random variable distribution that may be known or unknown. Using a sample that matches the random variable, suppose mu X is the mean of X, sigma X is the standard deviation of X. If you draw random samples of size small n, as n increases, the random variable sigma X consisting of sums tend to be normally distribution, okay, with a mean which is n times mu X, and the standard deviation is square root of n times sigma X. So the central limit theorem for sums says that if you keep drawing larger and larger samples and taking their sums, the sums form their own normal distribution, okay? The sampling distribution, which approaches a normal distribution as the sample size increases. Okay, same calculator, second verse 2, which is normal CDF. Okay. Find the probability that the sum of the 80 values. So an unknown distribution is a mean of 90, standard deviation of 15. Sample of size 80 is drawn randomly from the population. Find the probability that the sum of 80 values or the total of 80 values is more than 7,500. Okay. So we are going to use the information from the previous. Okay. So, okay. So we are, so it is second verse 2, more than uh, some of the 80 values. Okay. And so Okay, some of the 80 values is more than 7,500. So your lower is 7,500, your upper is 1, then second button and comma button, which is on top of the 7 button, gives you the E99. What is your mean? Your mean is 80 times 90 or 7,200. And what is your standard deviation? Is 80 times 15, okay, which is 1,200. And you do paste, enter, and enter. And the answer is 0.401, or 40% of the samples will be above 7,500. Find the sum that is 1.5 standard deviation above the mean of the sums. Okay, 1.5 standard deviation. Okay, so above the sum of the standard deviations. So that means we need to know the area to the left, 1.5. We know one standard deviation is, what is it, 0.34 plus 0.5. So it is 0.34 coming from empirical rule, which says that approximately 68% will be between one standard deviation. So 68, half of 68 is 34 plus 50% on the left. 50 plus 34 is 84, and 0.5 further. Okay, so what are we talking about? Okay, okay, so we go second verse in norm. Area to the left is, I told you it's 0.34 plus 0.5 is 0.84, plus on top of that you add say I would say another 8.08, so 0.92. Okay, why 0.08? Because it's come up to one standard deviation, it is 0.84. And then you're adding 0.5. Okay, so it's half. Okay, so should be 0.93, I think. This mean is 90 times 80, 7,200. And standard deviation is 15 times 80 is 1,200. And paste, enter, and enter. And it is 8970.95. Okay. And here they find a distribution to the calculator. Okay. We will not worry about it. Okay. Use the central limit theorem to solve real-world applications. So it is important for you to understand when to use central limit theorem. If you are being asked to find the probability of the mean, use the central limit theorem for the mean. If you're asked to find the probability of a sum or total, use the CLT for sums. This also applies to percentiles for means and sums. Okay. Okay. In the United States, someone is actually assaulted every 2 minutes on average, according to number of studies. Suppose that the standard deviation is 0.5 minutes and the sample size is 100. Find the medial, first quartile, third quartile of the sample mean times, okay? So let's do it. Second verse 3, now. Median is 50th percentile. So area is 0.5. What is the mean? It's equal to the mean of the population, which is 2. What is the standard deviation? It's 0.5 divided by square root of 100, which is 10, which is 0.05. So the median will work out to, so 50% area below it. Median is 2, okay? Then the first quartile area below is 0.25. So second verse 3, area is 0.25 and the other things do not change. Paste, enter and enter. And what? 1.96. Okay. Third quartile, area below is 0.75. Second, verse 3, third quartile area is 0.75. And you go paste, enter and enter. And it is 2.03. Okay. So that's part A. Similarly, you can continue with the other parts. As I said, I posted some link to videos which show you how to work with these problems. Okay. Okay. This normal approximation to binomial. Let's see how they do it. What do they say? Historically, being able to compute binomial probabilities was one of the most important applications of the central limit theorem. Binomial probabilities with a small value of for n, say 20, were displayed in a table or book. To calculate the probabilities with large values of n, you had to use binomial formula, which could be very complicated. Using the normal approximation to the binomial distribution simplified the process. To compute the normal approximation to binomial distribution, take a simple random sample of the population. You must meet the conditions for a binomial distribution. Remember, binomial two outcomes, success or failure. You must meet the conditions for a binomial distribution. There are certain number n of independent trials. The outcomes in any trial are success or failure. Each trial has the same probability of success P. Recall that if X is a binomial random variable, then X is a binomial random variable B. Okay, sample size is N, or sample size is N, and P is the probability of success. N is not the sample size, N is the number of trials you're going through. The shape of the binomial distribution needs to be similar to the shape of the normal distribution. To ensure this, the quantities NP and NQ. NP means N times probability of success, which is total number of success in N trials, and NQ, Q is 1 minus P, or probability of failure. N times Q is total number of failures in N trials, must both be greater than 5. Okay, N times P greater than 5 and N times Q greater than 5. The approximation is better if they are both greater than or equal to 10. Then the binomial can be approximated by a normal distribution, mean mu equal to NP, and standard deviation sigma is equal to square root n times P times Q. Remember that Q, as I told you, is probability of failure is 1 minus P. In order to get the best approximation, add 0.5 to X or subtract 0.5 from X. Use X plus 0.05 or X minus 0.05. Okay. The number 0.5 is called the continuity correction factor and is used in the following example. In a city, 46% of the population favored the incumbent, Don Morgan, for mayor. A simple random sample of 500 is taken. Using the continuity correction factor, find the probability that at least means to greater equal to 250. Okay, favor. Okay, so we are going to use a normal approximation to this binomial distribution. Our probability of success is 46. So first thing we will multiply is n times p. Remember, 46% is 0.46. So 500 multiplied by 0.46 is 230, greater equal to 10. And what is 500? Then put a left parenthesis, 1 minus 0.46. That's a probability of failure. 1 minus probability of success is 270. Both of them greater equal to 10. So you can use the normal approximation to binomial. Okay. So now you need to know the mean and the standard deviation of this normal distribution. So mean is n times p, which is 500 times 0.46, which is 230. What about the standard deviation? It is second, then x square. Second button on the top left, then x square, first column halfway down. Gives you the square root. Inside the square root, n is 500. times P is 0.46. Then left parenthesis 1 minus 0.46. Then right parenthesis. So everything inside the square root. 500 multiplied by probability of success 0.46. Then left parenthesis, no multiplication sign here. Left parenthesis 1 minus 0.46. Right parenthesis and hit enter. So standard deviation is 11.14. At least 250 means 250 and more. Minimum is 250. So we will use a continuity correction factor of 0.5. So because we are including the 0.250, we have to go 0.5 below. Okay. So my lower will be 250 minus 0.5, which is 249.5, and my upper will be 1E99. My mean is 270. My standard deviation is 11.14. So I go second, verse 2. My lower is, I told you 250 minus 0.5 is 249.5. Why this correction? Because it ensures that we will include the point of 250. What is my upper? 1, then second, comma. Gives me the capital E, which is exponent 99. What is my mean? Is 270. What is my standard deviation? 11.14. Then I go down to paste, enter, and enter. And it is 0.967. So 96.7% probability that at least 250 will favor Don Morgan for mayor. Okay. So this is the end of it. I stop here today. If you have any question or comment, write me a note. I'll get back to you as soon as possible. If you like this video, please give me a thumbs up. If you like this video, share with your friends. You and your friends, please subscribe to my channel, Math Science Topia, where I have solved all kinds of statistics problem in the playlist statistics problems. So please subscribe to my channel by hitting the red subscribe button at the bottom right corner, and then you can access the stats problem playlist where I've solved all kinds of statistics problems just for you. Okay. And do not forget to watch me tomorrow when I'll be back with another problem, another solution. Thanks for watching. Have a nice day. See you tomorrow. Take care.